All right, well, I wanted to say just a few more things about acid-base chemistry that I realized we didn't do and that were sort of important. So,
Is that recording still?
yeah, I'm recording now. Yep. So, and I think this will help you mostly if you're TAing 351 or in 352 in the future. If you're comparing the strength of a neutral acid, it's often best to rationalize acid strength based on the stability of the conjugate base. Okay, so for example, if we were going to compare the acid strength of these two alcohols, it would be easiest, and I'll just show you what their acidities are in terms of their pKa's. It would be easiest to do this by drawing the conjugate base and asking the question, which is more stable? That is, which is better able to tolerate that extra electron density? And in this case, we'd say resonance, right?
Yeah.
But it could be any number of things. Resonance is a great explanation. Electronegativity of the atom that bears the negative charge can be an explanation, provided that you're in the same row of the periodic table. Because it turns out size and polarizability matters a lot. So the pKa of just a regular alkane is in the range of 40 to 50. I'm just going to say 50. So that's like never in the age of the universe has an ethane molecule dissolved in water lost its proton, right? Never. Or rather, the probability is so low that if it happened, it would only happen once or whatever. I don't know. So you can rationalize that again by comparing the strength of comparing the stability of the conjugate base. Here it's carbon that bears the negative charge. Here it's oxygen. Oxygen's more electronegative, right? Okay, not a big problem. Another reason, another reason why one acid might be stronger than another has to do not with electronegativity, but let's see, 4 and minus 13 or something. What's that?
The size of the shell?
Size, yeah. So F minus versus I minus. It's importantly here not electronegativity. Because actually iodide is way less electronegative than fluorine. But the point is that iodide is larger, that if you look at bond dissociation enthalpies, the bond in HI is weaker than the bond in HF. And that has to do with the fact that iodide is larger, whereas fluoride is smaller. So it's easier to break the HI bond because iodide is larger and the HI bond is longer and therefore weaker. The other reason you can rationalize it is just by saying that iodide is large and the negative charge is therefore spread out over more space than in fluoride, where it's the radius of fluoride is pretty small. Okay, so that's, let's see, is that everything? Right, there, and let's see, the couple of more explanations in terms of comparing the strength of acids by looking at the stability of the conjugate bases. You can consider the presence of nearby electronegative groups, for example, and even electrostatic effects. So here is an amino acid, glycine. The pKa of this proton is 2.3, whereas the pKa of propanoic acid is 4.8. And of course, the reason is that if you lose a proton from glycine, the molecule's neutral, versus if you lose a proton from propanoic acid, the molecule's negatively charged. So the difference here would be, we would call that an electrostatic effect. But closely related to that is the idea that if you have a nearby electronegative group, the presence of that group will stabilize the conjugate base by helping to pull electron density away via a dipole from the place where the negative charge is. Okay, that sound familiar?
Yeah.
Okay, last on our list there is just for reasons to comparing conjugate bases. You've got resonance, electronegativity, you've got size and bond strength, you have an electrostatic effect, you have, we call this an inductive effect. Man, sorry that my penmanship is so terrible. I can't write fast and write neatly. And then lastly is to consider the, yes?
Sorry, can you explain this first the electrostatic effect with the positive and nitrogen?
This one?
Yeah.
Okay. So look at the stability of these two. Which do you think is more stable and why? You see how when this acid loses its proton, you get a negatively charged conjugate base. When this acid loses its proton, you get a neutral conjugate base. So that negative charge is stabilized by the presence of the nearby positive charge. And truthfully, there's also a dipole effect going on here as well, because nitrogen's more electronegative than carbon. Yeah. All right, so electrostatic effect and the closely related inductive effect. The last thing that I typically don't teach undergraduates in the chemistry course in OChem is the influence of solvation. And the idea is bulkier conjugate bases are harder to solvate. And remember, the point of solvation is to stabilize the negative charge via ion dipole type interactions. So as an example, you can look at pKa's for this series of alcohols, starting with methanol, ethanol, isopropanol, and T-butanol. And pKa's go from 15.5 to 15.9 to 17.1 to 19.2. And the idea here is that as you introduce more alkyl groups, it gets harder and harder for the solvent to orient itself around the negative charge and stabilize it, right? So it should be much easier for solvent molecules, in this case maybe water, to orient themselves around methanol than it is for solvent molecules to orient themselves around T-butanol. However, you can rationalize, the other way you can rationalize this trend at least here, is by saying, well, alkyl groups are electron donating, and therefore, if you donate electron density towards the place where there's a negative charge, the negative charge should be destabilized. So people can attribute this to poorer solvation versus better solvation, but you have to be just a little bit careful in the sense that people can all also rationalize this with the idea that alkyl groups are electron donating. Yes?
What about if the alkyl group extension is not forming branch, is a straight chain?
Right. If it's not a branch, if it's a straight chain, I think the pKa's, I don't have the numbers, but I think the pKa's vary less, especially in solvent, though actually the trend here is backwards in the gas phase. This is something your text points out. I didn't talk about it because the gas phase is not that interesting to most people, but it turns out in the gas phase, self-solvation is important. You don't have any other molecules around your negative charged conjugate base, and therefore anything nearby that helps to spread out the electron density via just induced dipole type things. And so the trend in the gas phase is actually reverse. It turns out that in the gas phase, this one's the most acidic because it has the most, it's largest, it has the most nearby groups whose electron cloud can distort itself to accommodate the negative charge. But your question was, well, what if I just continue on linearly instead of branching? And I don't think, beyond a certain point, I don't think it changes very much. Yeah.
It will probably be less than
you would think, yeah, you would think it would be less than 17. And you would think that in terms of sterics, once you get beyond here, once you get beyond that branching point, the stuff you're adding is far enough away so as to maybe not have a huge effect. Yeah?
What would a gaseous acid do? I'm just thinking that through, and I'm thinking like a cloud of face-eating acid. That's not right, but or is it right?
This is how the Joker got his smile or something like that, right? A cloud of acid. No, I think these experiments, so how do you determine gas phase acidities? Your text points this out. The nearest thing I can think of, I don't know. I want to say perhaps a mass spec experiment, but you'd basically want to do something called proton affinity, which is measure how much a particular anion wants a proton in the gas phase. And I want to say it's almost certainly mass spec's a part of that, but I don't know. I'm sorry. Yeah. But right in the gas phase, your acidity would be going from this to this plus really just proton, right? Yeah. And that's reasonable in the gas phase, though it's not in solution. So yeah, I don't know how to measure those. The other thing we ought to say is that, let's see, if you're comparing the acidity of cationic acids, like, for example, it's best to focus on the stability of the charged acid rather than the neutral conjugate base. All right. And I guess examples. All right, so the last thing we need to talk about from chapter 5 is something called hard, soft, acid-base theory. And this one's difficult. And when we're talking about hard, soft, acid-base theory, we're talking about Lewis acids and Lewis bases. Remember, Lewis acids are electron acceptors. They are, and Lewis bases are electron donors. We also say electrophiles for Lewis acids, and we say nucleophiles for Lewis bases. And if you think about the interaction between a Lewis acid and a Lewis base, you can think of it in a couple of different ways. One is mostly an electrostatic interaction. That is, cations are attracted to anions. You know, for example, sodium ion is a Lewis acid, hydroxide ion is a Lewis base, okay? And that the energy of this electrostatic interaction you've seen before, this is just literally Coulomb's law. So charge 1, charge 2, and then 4 pi dielectric constant, permittivity of free space, and distance between the two. And so types of Lewis acids and bases that have strong electrostatic interactions are generally small. They're generally non-polarizable. They generally have localized negative charges or positive charges, depending on whether you're talking about the base or the acid. And if there's, and the other thing we might add is that things that are good at the electrostatic interaction generally have a lower energy HOMO and a higher energy LUMO for the base and the acid, respectively. Okay, and then there's another way to have Lewis acids and bases interact. And actually, I want to take this one off the list. There's another way for Lewis acids and bases to interact, and that is through orbital overlap. Because, of course, we have seen before HOMO-LUMO type interactions. That is, you can imagine making a new bond by having the HOMO of a nucleophile, which would be 2 lone pairs, attacking the LUMO of an electrophile. So this might be some sigma star, say in some alkyl halide or something like that. And the energy of this orbital overlap interaction, remember that when two orbitals come together, you get one that's lower in energy and the other that's higher in energy. So the energy of stabilization for this orbital overlap, and your text doesn't provide any derivation for this formula they give you, it will come out of the same types of considerations that we did in chapters 14 and 1. 2 times Ca, which is the orbital coefficient on the atom that has the negative charge, and Cb is the orbital coefficient on the atom, sorry, A and B are for acid and base. So these are orbital coefficients, that is how much electron density is on the Lewis acid versus the Lewis base. And then the beta is the extent of overlap in space. And then finally, in the denominator, you have the energy difference between the acid and the base. This energy difference here. And you can see that ways to maximize orbital overlap are to increase beta, increase the energy that you get from overlap, or to increase beta, that is better overlap in space. Or you can decrease the energy gap between your Lewis acid and your Lewis base. And these are principles we've already sort of talked about, right? We know that sigma bonds are stronger than pi bonds. Why? Because orbital overlap between 2 sigma out orbitals is end on end and really tight, whereas orbital overlap between 2 p orbitals is side to side, not quite so tight. And we've also talked about in the 2 orbital mixing problem how if this difference in energy is smaller, then the strength of stabilization gets better. And Lewis acids and bases that tend to be good at orbital overlap are highly polarizable. They tend to have higher energy, highest occupied molecular orbitals for the Lewis base. They tend to be larger. They tend to have spread out negative charge or lone pair. For the acids, they would have a lower energy LUMO and would have perhaps a spread out positive charge or an empty orbital. And we're going to call acids and bases that are good at the electrostatic interaction hard, in part because you can think of them as hard little spheres that constrain the negative charge. And we're going to talk about Lewis acids and bases that are good at orbital overlap as soft. And perhaps soft because they're polarizable in the sense that you can think of the electrons, the extra electron density present in the conjugate base as being sort of squishy and easy to move around a little bit. Okay, so the overall energy of an interaction between a Lewis acid and a Lewis base is going to be going to have some term for electron repulsion that's going to be constant. Then we're going to have a term for the electrostatic interaction and a term for the orbital overlap interaction. And it turns out that things that are good at orbital overlap are also pretty poor at electrostatic interaction. You might expect that spreading out a negative charge would decrease the strength of the electrostatic interaction, and it does. You might anticipate that being small and non-polarizable and highly localized with a really sort of lower energy HOMO and high energy LUMO, that's going to make this number large, and then the overlap energy is going to be small. So the idea is that hard Lewis acids and bases are good at the electrostatic interaction. Soft Lewis acids and bases are good at orbital overlap. They're not good at each other's category. And so you'll tend to find reactions that involve hard Lewis acids and hard Lewis bases work better than reactions that involve a hard Lewis acid and a soft Lewis base. Similarly, you're going to find that soft Lewis bases and soft Lewis acids interact better than a soft Lewis acid with a hard Lewis base. I'm trying to remember, Professor Stowers once talked to me a little bit about this. Have you guys talked about hard, soft, acid-base stuff in 514?
We just took a test on it.
Okay, so what am I missing? Oh, okay.
Yeah, we didn't go in depth on like how it works. We just said this is hard, this is soft.
Okay.
You put it together.
Okay. So examples of hard Lewis acids. I'll just give you some examples. This isn't comprehensive. These might include actually a lot of cations. So lithium, potassium, magnesium, calcium. It also includes boron type compounds, Br3, and aluminum type compounds, like aluminum chloride. These are hard electrophiles. They have higher energy LUMOs or have localized positive charges. Some examples of some hard Lewis bases include anions, and especially first row atoms, first row anions where the negative charge is held on a very small atom. Even acetate tends to be a harder Lewis acid. Chlorine tends to be a harder Lewis acid. Lewis base. Water, the lone pair is localized enough, even though it's not negatively charged. Water is considered a hard Lewis base. Alkoxides, alcohols, and let's see, amines are also on this list. And there are some others. For soft Lewis acids versus bases, what are you looking for? The examples your book gives tend to be larger types of things, like transition metal elements, copper, silver, mercury. Not that you're going to encounter these a lot, although you will encounter palladium too. Neutral compounds like iodide or bromine that are electrophiles, they have a low energy LUMO. Carbines tend to be soft Lewis acids. Radicals tend to be soft Lewis acids. I'm trying to think if I'm missing anything. Soft Lewis bases are like you might consider thiolates or thiols, kind of like alcohols. Except the atom that bears the negative charge or the lone pair is smaller. Iodide is actually a good soft nucleophile because of its polarizability. And there are other examples. Cn minus would show up here. Probably azide would show up here. And there are other examples your text gives, but I think alkenes can be fairly soft Lewis bases. Benzene can even be a soft Lewis base, but those are some examples.
Is there a trend, strength, or for this example, do they follow any concept?
Oh, in the way I've listed them, do they follow? Yeah, in no particular order.
So can you determine which one is harder?
Well, at least for the hard acid base, you're going to basically use, well, for the hard Lewis bases, you can rationalize this mostly in terms of electronegativity. In other words, you would predict that fluoride would be a better, you would predict that water would be a better nucleophile. I'm sorry, you'd predict that hydroxide would be a better nucleophile than fluoride because fluoride's negative charge is lower in energy than hydroxide's is because of electronegativity. You would similarly predict an amine would be more nucleophilic than an alcohol because because nitrogen's less electronegative than oxygen, and therefore the lone pairs on the nitrogen are more nucleophilic, higher in energy than the ones on the oxygen. So you can rationalize nucleophilicity among the hard acids and bases simply by considering mostly electronegativity. For soft Lewis bases, you're going to think about basically size and polarizability. How easy is it for the negative, how large in space is that negative charge spread out? How easy is it for that negative charge to distort its distribution through space to attack an electrophile? Okay, I don't know. That concept shows up and you'll hear people talk about it in talks, you'll encounter it in papers. I don't necessarily see it as useful for me to ask you a question on a take-home exam about which of these is a hard acid versus which of these is a hard base, because you can just come to your notes and look. And anything you can look up is not that great, but if you can compare, if I were to ask you to compare two different hard bases and you tell me which one is more nucleophilic, or compare two different soft bases and you could tell me which is more nucleophilic, that's the kind of thing that would be useful in your future career. So I've spent way too much time on chapter 5, I'm sorry. That's a troublesome, hard soft acid base theory is sort of troublesome, and again you'll see it come up. I just want you to know what people are talking about when they mention it. For example, when people discuss Lewis acid catalyzed reactions, they might say, oh, well, we tried some harder Lewis acids and then we tried some softer ones, and you'll know sort of what they're talking about. Okay, chapter 6 is stereochemistry. Are you ready for your mind to be blown? Stereochemistry is mostly about blowing your mind. Okay, so need to know a couple of things to begin with. Stereoisomers means what? Same mass, same formula, same connectivity, different 3D shape, I guess is maybe how we would call it. Yeah? And typically we don't mean conformational differences here, though that gets a little bit messy. The term stereoisomers encompasses all types of molecules that have the same connectivity but are nonetheless different in the arrangement of functional groups. And there are only two kinds of stereoisomers. You got two choices. One is diastereomers, and the other is enantiomers. And the only way to distinguish between these is enantiomers are mirror images of each other. but nonetheless not the same. So, as an example, I could show you the following two molecules. Maybe I wanted that one to still be down. What is the relationship between these two molecules? Diastereomers. Good. How can you tell? Okay, there's a lot of ways you could tell. The fundamental definition is they're not mirror images, but they are still stereoisomers. The other way you can tell is that if you identify the stereocenters, one, but not all of them, is different. And you can assign R versus S if you want to. We're not going to talk about that because you should already be good at that. A different question, and somewhat unrelated, is which of these is chiral?
This is chiral.
Which one? The one on the right you're saying is chiral?
Yeah.
And
This is not chiral.
the one on the left is, you're saying, not chiral. Why is that not chiral? It's a meso compound. It has a plane of symmetry. Yep. So if you put a mirror here and draw the mirror image, it is its own mirror image, right? Okay. So so you can see that the relationship between chirality and stereoisomers is a little complicated. You can be a stereoisomer and not be chiral at all, right? For example, this diastereomer that is not chiral. If you are chiral, you have to have an enantiomer because you're not the same as your mirror image, right? Some other examples of...
I think I need to have is it 4 different atoms attached to the carbon?
Okay, so stereocenter is another definition. We'll talk about what that means. Stereogenic center is the technical term, but most organic chemists will use stereocenter. Somebody who uses stereogenic center is usually trying to show off. But out of favor, though you will hear people use it, out of favor is chiral center, for the very reason that you can have a stereocenter and not be chiral. Yeah. So, again, you will hear respected chemists say chiral center, and you just have to shrug your shoulders and say, well, that's a remnant of an older time, because I'm going to show you can totally be chiral without stereocenters. And you can have stereocenters and not be chiral. So we prefer not to use the term chiral center. Now, what is a stereocenter? Well, in the context of carbon, you're thinking of an sp3 hybridized carbon with 4 different things. We might need to expand that to say sp3 hybridized atom in general, because there are such things as nitrogen and sulfur-based stereocenters. However, I'm going to show you a ruthenium complex. And I'm not good at this, so don't laugh at me too much. Rachel and Alex who are in 514, you can tell me what I'm doing wrong. Here's an octahedral ruthenium complex. And we can make a stereoisomer simply by trading some positions, like if I put this axial chloroligand in a more equatorial position, those two are now stereoisomers. And what's the relationship between the two? They're not mirror images of each other, certainly. they would be called diastereomers. And therefore we could say that the ruthenium is a stereogenic center. Though I don't know that I don't think people assign configurations for octahedral atoms. I mean, it's possible that they do. A related issue would be whether either of these compounds is chiral. To determine that, you would have to make the mirror image and then see if you could see if the molecule was the same as its mirror image.
So this is chiral. There's a stereogenic.
I don't know. So if you want to ask, are either of these things chiral? I would say the one on the left is not chiral because it has a plane of symmetry right there.
Yeah.
Everything on the left is a reflection of everything on the right. In terms of whether this one is chiral, I would also say not, because it has a plane of symmetry that intersects the following atoms: this oxygen, that oxygen, that oxygen, and that chlorine. And then left and right is the same thing. So both of these are not chiral. Nonetheless, they are diastereomers. And then the classic example, I love to do this question on a test for undergrads in my OChem class. The classic example is alkene stereochemistry. I do disclose my evil tricks ahead of time, but I do rejoice in this particular one. I ask, what's the relationship between those two? And people that are just looking at stereocenters are like, oh, I know this one. They're enantiomers. They have opposite configurations at their one stereocenter. Not so fast. Enantiomers have to be mirror images, and a mirror doesn't change alkene configuration. This is an E alkene. This is a Z alkene. Issues of E and Z configuration in alkenes are always, always, always diastereomers, independent of whether there's any stereocenters in the molecule. Okay? Nasty trick, right? So now if you're TAing for 351 or 352 and you need a practice problem to review for stereochemistry, try this one. It's really fun. But this, we can expand our definition of stereogenic center to include the alkene, as it's no longer a center, it's not a single atom, but it is a place where you can have stereochemistry, and so we will call this a stereogenic unit. Most people do not call alkenes stereocenters, but you can call it a stereogenic unit. All right. Are you ready? Oh, dang, 1 minute left. Are you ready for something that is chiral but does not have a stereocenter?
Okay.
I'll just draw it, and then we'll have to wait until Friday, wrestling with it in your mind. Allenes don't have stereocenters. There's no sp3 hybridized carbon. Nevertheless, the following molecule is chiral, and the following two molecules are enantiomers of each other. So, so you should play around with that and convince yourself that you may have to make a model, twist it around, and if you don't have access to models, come to my office and we can play with the ball and stick models. But try as you may, there is no way to make those two the same thing.
So that carbon in the center is not a plane of symmetry.
The carbon in the center is not a plane of symmetry. So you might say, is the plane of the page not a plane of symmetry? And the answer is no, because you're fine all the way here, but then here the proton and the methyl group are different, right? And similarly, you could say, well, what about this plane? Isn't that a plane of symmetry? No, because the proton and the methyl group are different.
Is it because you can't rotate the allene at all?
Yeah, there's no rotation around double bonds, at least not at room temperature.
So if you want to say you're attached to C2H4 on one side, C2H4 on the other side, that won't work as plane of symmetry. Like
If I had methyl groups on both of these carbons, it would not be chiral.
yeah, I'm talking about what you have on the right being the same as what you have on the left.
It would
They're
still be
different-
chiral.
different atoms.
Yeah, it would still be chiral if we did this.
Really?
Yeah. Those are still enantiomers. So, anyway, give that some thought, convince yourself, because what we're going to conclude is that this allene is also a stereogenic unit, not a stereocenter. And we're going to need a new way of talking about the stereochemical configuration of that unit, because you can't assign R versus S. Or you can, but the more technical way to assign stereochemistry is with two new letters, P and M. I don't know.
Papa and mama.
That's right. All right, we'll see you next time.
We brought up alleys.